the Museum of Art of Rio. It's my pleasure to introduce to you the talk of this last session by James Bergstra. Thank you very much for accepting the invitation. We are very happy to have you here. Deep learning is a subject that many people in this room are interested. In my lab, especially in reasoning for complex data in Campinas, we have been using your library for some time. For those of you who don't know, James is one of the authors of Theano, the metaprogramming system for Python that target GPU for high performance computation. And he is now a postdoctoral fellow at the University of Waterloo in the Center for Theoretical Neuroscience. He was before that, he was in the Holland Institute for Science at Harvard University. He has interest in deep learning, learning algorithms, visual system models, Bayesian optimization, high performance computing, and also music information retrieval. So without further ado, James, please.
Yeah, thank you very much. That's a great introduction. I'm very honored to be here and also very nervous. So thank you very much for coming. I'm not going to talk at all about music information retrieval today. I'm going to stick to those other things. The talk is titled Big Data, Deep Learning, and Hyperparameter Optimization. And I hope by the end of the talk, these buzzwords won't feel so buzzy anymore. They'll actually mean something. So let's get started. I just, in case you haven't heard the term deep learning before, it's a recent term that kind of got coined in the popular press, I think mostly because of Geoff Hinton, who wanted to draw a distinction between what he called shallow learning, which was the support vector machines, that he had like a personal campaign against them, and his own research, which was multi-layer neural networks, so he thought he should call his systems deep. And around 2012, they became very popular to talk about in like the New York Times all of a sudden. So everybody who had been doing their PhD in this, spending years going to conferences and talking about technical stuff, then you see this stuff appear in the New York Times and the New Yorker, and it's very strange to see them discuss your research in the popular press. So here's some of the titles that came up all at once. Is deep learning a revolution in artificial intelligence? It's like pure clickbait. Scientists see promise in deep learning programs, and the learning machines is written up in Nature News. And finally, last year, Geoffrey Hinton was hired by Google Labs, and so now he works as an employee at Google. So what happened? I'll try to explain a little bit about this. I structured the talk into three parts. The first part of the talk is about the connection between big data and deep learning. And I'll explain why I think these things are quite closely related. The second part of the talk will be a fairly short, there's not equally spaced pieces here. The second part is going to be about how to get started doing deep learning using that library that was just mentioned called Theano. It's a fairly short section, but it'll show how accessible it is to do deep learning. And then the last piece is hyperparameter optimization. And I'll spend a bit more time on this hyperparameter optimization part because that's been a bigger focus of my research for the last 2 or 3 years. So big data. This is a slide from 2001 by in a paper from a natural language processing community called the very large-scale, oh shoot, I forget the name of the paper. I'm sorry. Sorry, Banco and Brill. But this paper is about disambiguating ambiguous words that have many meanings. So this is a classification accuracy, and they solve this method with classifiers. And so the more data you use in a classifier, the more accurate it gets. But at the time, most people don't publish about how much data they use. They published about which algorithm they used. So somebody would publish about how they used a decision tree. Somebody else would publish about how they used such a kernel for the support vector machine, and so on. And what they were showing with this figure is that each algorithm corresponds to a red one of the lines, and the axis is how many words they trained on. So you can see. Well, okay, I won't use the clicker. I'll just point. So you can see here, if you just looked at this many words, you'd see that this memory-based approach is way better than the perceptron, and way better than this Winnow approach. But as you move to the right across the graph and you use more data, all the lines go up by a lot more than was the big difference between the algorithms if you just looked at a small amount of data. So the effect here is that data is sort of more important to the accuracy of your method than what your method actually is. And this sort of flew in the face of the way work was published at that time. And so I want to use that definition to explain like what my definition of big data is. And my definition of big data is that it's so much data that any algorithm that can actually use it all outperforms algorithms that require subsampling of the data. And so when you get into that regime where the algorithm you're going to use can't really cope with what you have, you're in a big data situation. So how to keep getting better performance as you get more and more data becomes a question that's of paramount importance. And so what we want is algorithms that have constant time prediction on test data. We want for the complexity of your model to be able to capture more and more accurate predictions to increase as you have more data to refine it. And we want a model that can be improved also by unlabeled data. And multi-layer neural networks have been the tools that have really succeeded in this regime of huge amounts of data. And these multi-layer networks are the deep learning. So that's what's been leading to 40% improvements in error rates in ImageNet, huge improvements in large-scale object recognition. Speech recognition's got quite a bit better by using deep learning approaches and huge amounts of previously recorded speech data. And even in natural language processing, deep learning approaches are starting to unify all the different kinds of problems that people tackle in that domain. So this is a picture of a prototypical neural network from like 1986, probably. This is the way they're often drawn with these circles on the left would be like input variables that you're going to try and predict something about. These weights correspond to a linear projection of those inputs. These middle dots are performing non-linear kind of squashing operations like a neuron is supposed to be able to do. And then you repeat that a couple of times, and eventually you get a linear classifier, for example. That's been a really popular kind of readout. And so that's a simple kind of neural network. Also, people talk about convolutional networks, where it's the same kind of thing, except for the little networks are kind of overlapping, and they each transform parts of images. I'm not going to really explain how exactly a convolutional network works. I hope it's familiar to most people in the audience. And so with these two kinds of networks, I just wanted to sort of lay out like what have been the changes in the field that led to deep learning. So like all the way back in the 60s, we have the early work on the neural networks. In the 1986, that was when people started using gradient descent and backpropagation to tune the things. Convolutional networks are also from the 80s. And then there was sort of a lull where there wasn't much attention paid to the neural network research programs. Then in 2006, there was a breakthrough in using semi-supervised training methods. So if you've heard about deep belief networks or restricted Boltzmann machines, those kinds of autoencoders and that kind of stuff, those were being introduced around this time. But they haven't actually stuck. They were sort of a turning point to bring people's attention back to the use of neural networks. But those algorithms are not actually the ones that are delivering huge performance on ImageNet, for example. DBNs are not used. Restricted Boltzmann machines are not used. Autoencoders are not used. What is used is the rectified linear units, which is just like a slightly different shape in the nonlinear activation function, and GPUs that go about 10 to 20 times faster than the CPUs that used to be used. So the big difference, well, drop out too. The big difference is just that these days we can train on hundreds of thousands or millions of images, and that just wasn't possible in the 1980s. So neural network researchers just didn't know how good their models were. This graph on the right is the increase of speed of graphics processing units. And that's been the real driving force in deep learning. So I'm glossing over what is usually talked about as the advances in neural networks, which are like dropout and max out and restricted bolus machines, and auto-associators, and so on. But I think those are actually not the big story when it comes to deep learning. Deep learning is about using big data. With that said, there is still a hypothesis about the relationship between those multiple layers in a neural network and the way people form complicated representations of things in their minds. The idea is that, and it's supported by a lot of research in the visual cortex especially, your retina picks up something like pixels, it's processed by your V1 visual area, and then it kind of cascades through the visual system, and ultimately in IT, you get things which can be linearly related to object classes. So the human visual system does kind of look like a feed-forward neural network. And the hypothesis is that training in a supervised way, a completely artificial neural network based on a whole bunch of labeled images, kind of gets at the same effect as living in the world with an actual brain. And that's a huge hypothesis, but as it turns out, networks with multiple hidden units, hidden layers, are actually the ones that are making breakthroughs. They are reaching human-like and monkey-like performance in a lot of visual recognition tasks. And deep recurrent networks, such as the one coming out of my group in Waterloo with Chris Eliasmith, do label. These are big recurrent networks that are able to simultaneously model vision and action with an arm and some amount of cognition about reasoning and so on. So all these networks do exist, and they are kind of coming together. So even though the idea that training on a huge labeled data set is not at all obviously related to what actually happens to humans in the world, that is still something which seems to be coming together to be true. So how to actually get started with deep learning kind of means just training a neural network the way you probably learned how to do in your undergraduate course. But it has to be done in a way that can be amenable to really high performance computing. So don't start from scratch. Use a tool like Theano or PyLearn 2, or use the Torch tool that came out of New York University. Use GPUs for training. So we're talking about like the best GPUs that NVIDIA typically has for sale. Plan to use a lot of data. If you don't have at least tens of thousands of examples of the kind of function input-output mapping that you want to learn, deep learning solutions are probably not the answer you're looking for. Budget hours or days of training for that many images. So these things have to run for sometimes up to weeks at a time to get state-of-the-art results on large data sets. And there's several guides here for how to get started with like various tricks of the trade about how to initialize weights, how to set hyperparameters, which I'll come back to in a bit, how to train some of the components of a neural network, and then lastly, which I'll spend a lot more time on in this talk, optimize the hyperparameters of your model. So that was just like a really quick survey about what deep learning is about. I'm not going to spend that much more time on it now. I'm going to move on with how to actually use the Theano library, which I wrote, and then I'll move on to hyperparameter optimization. So actually, I should pause. I'm going to put up this overview slide a couple of times as I go through. I'll stop each one of these section boundaries. And if anybody has any questions, I know what I've presented so far is super high level, so you might not have any questions, but at every point where I get to the next kind of piece, feel free to put up your hand, and we can have questions about that piece. So if anybody does have any questions about the first part, I would invite you to ask them now, or otherwise we can just deal with it later. All right, I'll move to the next piece. So what's Theano? Theano is a great tool for neural network research. It's a language and a compiler for doing vector mathematics in Python. And it's been used as the foundation for the PyLearn 2 deep learning library. The idea of using Theano is to describe computations symbolically, which is quite unlike what Python computations are usually about. And actually, can I just get a quick show of hands? Does anybody in the audience use Python on a regular basis or know what it is? Lots of people. All right, that's good. So unlike using NumPy, which is the default mathematics library for computations in Python, Theano allows you to auto-differentiate costs. So you really can't think about auto-differentiation very easily in terms of NumPy, but Theano will let you do it. And the other big advantage is that Theano can allow you to switch between using the CPU and the GPU for computation without having to really change any aspects of your code. So it's been used quite a bit for deep learning, and it's a fairly active project. I'm not as involved with it now as I used to be, but it's still thriving under the watchful eye of Yoshua Bengio at the University of Montreal. So documentation is available at this website. Here's a project link. There's a various community resources to look at. I'll put these slides up after the conference so you can have a look at these things. I just really want to mention, though, that Frédéric Bastien and Olivier Bergstra are the main authors on some of the early work on Theano, and they've been hugely instrumental in getting it to where it is. So if you want to make a deep network in Theano, this is one way to do it. This is the whole. This is a multi-layer perceptron in one slide, and just because I think Theano is so great, I will spend a little bit of time going over how this works. So the way you set up a computation in Theano is to create symbolic matrices. So like this X and Y here, they are placeholders for values which will come soon. And these shared variables here, they are also symbolic values, except that they're initialized with the parameters of a model. And so it's like putting NumPy arrays into kind of Theano land. There's a memory space that corresponds that Theano manages, and these shared variables can be allocated either on the host, which would be your CPU, your conventional computer, or they can be actually allocated on the graphics processor. So from this point of view of this code, you can't tell the difference, and that's the idea behind making Theano easily switch between CPU and GPU. But with an environment variable that you set when you run the program, that'll choose where it gets allocated. So this creates the models of a neural network that will work on, I think it'll work on 100 examples at a time. So this W matrix is this piece here. So this will be the W, and this will be the V. So the idea, I'm being directed to use this thing. All right, so this is the W part, and this is the V part. So if we switch fast forward into the code example, then we're allocating enough weights to transform a 100-dimensional input, like you have 100 dots on the far left, into a 500-dimensional space of neurons, which is the middle set of dots in that last picture. And then this last part, V, projects your 500 neurons into 10 possible classes. So we're setting up to do like an MNIST kind of classification here. To actually describe what your deep model is, you build a symbolic graph on top of the symbolic variables. So these operators here, like the dot means a matrix product, tanh is a compressive nonlinearity that implements a transfer function in neural network. these things don't actually do any computations yet because W doesn't have any value. Sorry, X doesn't have any value. So what happens is that you just build a kind of bunch of pointers and data structures saying that if I was going to run this, I would do a matrix product, and then I would do tanh, and then I would do this addition, a dot product, a softmax operator, which is used for classification. And then, so this is a symbolic description. I'm getting closer and closer to it with this laser pointer. There's a symbolic description here of what your prediction of your network is, and here we have a symbolic description of the loss function that you optimize to train the neural network. And so when you differentiate, so this builds a symbolic account of the computations involved in training a network, and this line here is a symbolic gradient that goes back over the graph you just computed and produces a bigger graph that also has nodes that correspond to how to compute the gradients. So this gradient operator takes the loss and gives you back gradients with respect to W. The B values here, which are, the mnemonic is that W is for weights, B is for bias, and then V just comes after W and kind of looks like it, and C comes after B. So these are also biases, and these are also weights. There's a lot of code online that this will help you understand. So then you get all these gradient terms here, which you can plug into a function. And so this is the last part of Theano, which is unlike NumPy. When you call a function at this point, you're asking Theano to look through the symbolic graph that you just created and turn that into a callable object that will actually do the computations corresponding to training your network. So we're asking it to produce a function that acts on numbers for x and y, returns numbers for the corresponding loss, and while it's at it, it will also do these updates. And what these updates mean is that we're going to replace W's value with a new value that's obtained by subtracting a little bit of the gradient from the old value of W. And the new value for B is going to be its old value minus a little bit of its gradient. So this is a gradient descent update that implements a stochastic gradient descent algorithm, and it's built right into the definition of the function. And the reason why this is part of the interface of Theano, and the reason why I'm mentioning it, is because if you're not careful about how you implement computations on the GPU, you end up having to transfer numbers from the GPU back to the host, back to the GPU, back to the host. And if you ever have to do that, that usually ruins the whole point of using the GPU in the first place. So this is a bit of syntax that we've added to the library so that you can update things in place without having to transfer them around and waste time. So this kind of function definition works pretty fast. Sorry, the result runs quickly, but what the function actually does is it also, in the process of doing code generation, it does some analysis of your graph as well. So it's kind of an optimizing compiler. It eliminates duplicate expressions, kind of reorganizes your graph into a canonical way. It does some clever tricks about stabilization. Stabilization of arithmetic is really hard, so we don't get all the cases, but we get a number of them. It specializes a lot of special cases of pointwise functions, and also uses, I'm not sure if, does anybody actually suffered through the use of BLAS operations? You have, it stands for Basic Linear Algebra Subroutines, I think. It's a Fortran definition of linear algebra terms from like the 1800s or something. And it's still in use today, and it's kind of hard to use. And so we just wrote in our code that the dot product between the x and w should be used for calculating the hidden units. Whereas actually in the code, that turns into some kind of hybrid matrix multiplication, scaling, in place, weird operator that the hardware actually does really fast. And then finally, we transfer the results to, do code generation for GPU. And then that's actually what that function call does. So sometimes when you call a function, that last line, that can take a while, because it actually has to do some analysis and compilation and stuff. So you spend some time doing the compilation itself, but then when you run it, it's fast. So this is some benchmarking we did a couple of years ago against some other ways of implementing neural networks, like on MATLAB or with Torch 5, which is the previous version of Torch. The Torch guys are really competitive, so as soon as we published this result about how we were so much faster than Torch 5, they like re-implemented all of Torch. Now Torch is really fast. So Torch 7 is okay to use, but Torch 5 wasn't all that great. On the GPU, it's way faster than on the CPU. This is a convolutional network benchmarking that we did. Yeah, it's fast. So just to summarize what Theano does, it's a high-level functional description of the kinds of computations you want to do. It uses that functional description so that you can implement symbolic differentiation. So much of deep learning is based on numerical gradient descent that having a tool that automatically gives you gradients is a lifesaver. It rearranges expressions for speed and stability, and yeah, it compiles things to machine language. It uses the GPU, and since you write your program once in Theano and the compilation continues to get faster and faster, then you get better performance over time. So that was Theano. Theano makes building models easy, and running them, and training them, and so on. And so now the question I want to spend basically the rest of the talk on is, what model should you build? And that's the segue into the last piece of the talk about hyperparameter optimization. I'm going to use the terms hyperparameter optimization and model selection interchangeably. I'm going to explain how I think of model selection as an optimization problem. I'm going to talk about random search versus grid search. They're different. And I'm going to talk about large-scale model spaces and how to optimize them with an algorithm that I developed called the tree of parts and estimators, aka TPE. So that's what's coming up, but if anybody has any questions about Theano, then they can ask them now. So the question was, in the example that I'd given, I'd hard-coded a learning rate of 0.01 or something like that into the update expression. So the observation was that I had hard-coded this procedure, and the question was, can you use better optimization methods? Is that fair?
Yeah, sure. And I'm pretty naive, so if it's a stupid question, I'm sorry.
It's not. It's a good question. So there's actually two kind of responses to that. The simple, sorry, there's a joke from last night's dinner that just came to mind. There's a short answer and a long answer. The short answer is yes, but there's actually two long answers. The hard coding of this procedure is obviously unnecessary. You could have, for example, another variable up here, which was the learning rate, and you could use that down here in place of this one. So you could have a step size that changes over time. You could have a time index up there, and then hard code a certain formula that changes the step size with time. That'd be another thing you could do. You could also have these terms here, the gradient expressions themselves, be the input to another component that figures out like conjugate directions, and then so there would be more logic in between the calculation of the raw gradient and the step that you should take. That's another thing you could do, and there's some support for that. The other kind of response to that question is that why would you want to? Because stochastic gradient descent is so great. This is making you laugh because it's stochastic gradient descent is kind of a naive algorithm. But stochastic gradient descent with a couple of tweaks that have to do with changing step sizes in a kind of smooth way and being a little bit adaptive about it. The term momentum can come up from time to time. Is actually still the de facto gold standard way of optimizing neural networks on big data sets. Because a lot of the more sophisticated gradient descent mechanisms don't work on noisy stochastic loss evaluations. And so the increased speed you get from a more efficient algorithm is totally blown away by how much time it takes to actually compute one gradient direction. So if you had all of ImageNet with its hundreds of thousands of images, you can be almost done optimization by the time you get to the end of one pass through the data, rather than just starting. So that's something that's sort of a more subtle point about like how to train neural networks with Theano.
Thank you.
Okay, so I'll move on to the part on hyperparameter optimization. So just a sort of refresher, what is model selection by cross-validation? The idea of selecting a model by cross-validation is the idea of picking a model that just empirically works the best without reference to whether you thought ahead of time that would be a good idea. There's no notion of priors or penalties or information criteria and so on. The idea is just that you take data, your whole data set, and chop it into three logically distinct pieces with no overlap. And then you index all the possible models that you might want to pick from by some letter, like I'll choose theta here. The set of all possible models is the capital theta into which we're indexing. And the idea of cross-validation is to search the space of all the models for the one that works the best on the validation data. And in order that it works well on the validation data, it's customary to train it on the training data. And this is sort of the expression of that search procedure. We're going to search over all of theta, all those models, for the one that works best on the validation data. And then we're going to estimate our generalization performance by measuring that same loss function on test data. We're going to take that one that was the best and then try it down here. There are some variants like related to pack Bayes where you don't just take one, but for our purposes we're just going to take one. So the question is, how do you do that search implied by this argmin right here? The reason why it's important to think about that argmin is for science. Hyperparameter optimization is important because it's essential to the kind of insights that we want to learn from our machine learning experiments. So if I want to say, I've taken a statement about deep networks, but I'll actually just switch gears for a second and talk about like the old SVM versus neural network comparison. Which is better between SVMs and neural networks? The way to turn that into a testable hypothesis is to draw this circle here that corresponds to a universe of discourse that has all the SVMs in it and all the neural networks. And so if we imagine that all the SVMs are up in this part of the circle, and then all the neural networks are down in that part of the circle, then you can turn that into a more testable hypothesis, which is that like you could turn that into a statement like for sufficiently many data sets, namely the ones I care about, the best element of all the SVMs is significantly better than the best element of all the neural networks. So that's just a translation of that initial kind of intuitive claim. And to actually answer that question, we need to run two separate independent hyperparameter optimizations. First, we need to search over all the SVMs, and then we need to search over all the support vector machine, all the neural networks. And then we need to compare the result. And we need to do that for a lot of different data sets potentially. So that's kind of like the form that that argument should take. And it's really hard for people to do independent optimizations of things when they don't really have a formal notion of even how to do the first one. So that's why I was interested in studying optimization of hyperparameters as an optimization problem. It turns out that optimizing hyperparameters, even for simpler models, is pretty hard. And to tell a story about why that's true, I'm going to switch back into the example about neural networks. This is about the simplest neural network that you can draw. It's the sort of canonical one that I had on that previous slide, except for it only has one layer of hidden units instead of two. This is the kind of network that we implemented in the code sample. So this is a network that was proposed and popularized in the late 80s. We're going to compute 10H of a bunch of inputs, and then we're going to have a softmax computation on top. This simple neural network has arguably about 9 hyperparameters. There's the issue of like how to set the weights before you start the optimization process, because there's not a convex optimization, so depending on how you set up the initial conditions, you're going to get to different answers. So there's a couple of heuristics for how to do it. They don't give you the same quality of solution, so the choice of which heuristic to use is a hyperparameter. The number of hidden units is an important hyperparameter. That's how many green dots are in the middle and how much capacity your model has to model nonlinear effects in the data. The kind of activation function you use, whether it's like a sigmoid or a tanh, for example, makes a big difference to the quality. The number of examples you use at the same time when you're computing gradients for doing stochastic gradient descent can even make a difference. The learning rate makes a huge difference. Sometimes people reduce the learning rate over time. That's called annealing. And the point in optimization at which you start to reduce the learning rate and the number of steps you take to reduce it down to 0, that's a hyperparameter. If you want to regularize the model to have weights that don't get too big, that's at least 2 hyperparameters to say whether you're going to do it, and if so, by how much. There's a couple of different styles of regularization which aren't even mentioned. So even this like simplest possible version of a shallow neural network has these 9 hyperparameters, and that's actually a difficult space for a person to search. And if you're going to do a grid search to cover all those possibilities, there's several binary variables and a couple of real valued ones that you'd want to divide into a couple pieces. So that would be something like 16,000 grid points to cover this space of hyperparameters. Previous work with Joshua Benjo in 2012, we looked at how to optimize a deep belief network. I won't describe what it is, but it's kind of like a neural network, except it's got 3 layers instead of 1. And there's another algorithm called contrastive divergence that's used to train each layer as you go. So our parameterization of this one had 32 hyperparameters. And that was even like not really pushing the limits about how many things you could make a hyperparameter. This was sort of the bare minimum. Another example of hyperparameters is got nothing to do with deep learning, but it's been something I'm working on more recently with Brent Comer at Waterloo, and that's the idea of indexing a whole machine learning library as a hyperparameter problem. So, like support vector machines, there's a couple different kinds of kernels you can use, and each comes with its own hyperparameters. Decision trees have hyperparameters, neural networks have hyperparameters, k-nearest neighbors even has hyperparameters. There's other classifiers you could use. Data preprocessing often makes a bigger difference to accuracy than which classifier you actually choose, and data preprocessing totally has hyperparameters. And that's a kind of combinatorial situation where the preprocessing you do for your support vector machine might not be the best preprocessing to do for your decision tree. And even the choice of which classifier to use, you can treat that as a hyperparameter. if you don't really have a really strong feeling that your model totally corresponds to a radial basis function SVM, and then actually if you got a decision tree to work better, you'd be pretty happy with that, then you've expressed a cross-validation model selection idea, and you should use hyperparameters to describe the whole search space of like which classifier to use. And similarly, you can combine pre-processing algorithms and the choice of which kind of pre-processing to do. So this is the kind of space that I think about in terms of like searching with hyperparameter optimization. What kind of model should you build? Hyperparameter search spaces are interesting because there's many kinds of hyperparameter in them. You have categorical ones. So like the random seeds that you use to initialize your weight matrices. Those are hyperparameters. The kernel type in your support vector machine, totally a hyperparameter. Some of them are ordinal. So the depth of a tree, for example, is integer valued but ordered. There's several kinds of hyperparameters that have that flavor. They're different from real valued ones because you can subdivide them continuously. There's lots of different scalings that apply to different hyperparameters that only a domain expert would know. So if you give, as I did, to a very eager first-year undergraduate, the project of characterizing scikit-learn for hyperparameter optimization, just as an experiment, we came back with a very strange parameterization of all of the different options in the library because he didn't know that C should be positive, for example. He didn't know a lot of things that people start to take for granted after they spent a certain amount of time using these models. So I think that a big part of the job of describing a hyperparameter search space is to use your own knowledge that's been hard-earned over the years that you've spent tuning these things to inform what kind of hyperparameter combinations would be good, and to actually be able to encode those priors about what combinations are good in a way that algorithms can then take to the next level. So how to combine your own intuitions for what makes good hyperparameters with existing tools for numerical optimization. Anyway, that's a bit of a tangent to what's on this slide. Oh yeah, also nested conditional structure is very important. So that slide about all the different possibilities of hyperparameters in scikit-learn, we parameterized all those things out, and we got something like 56 hyperparameters that would describe all the support vector machines and decision trees and so on. But to just lay it on the table as a 56-dimensional problem is totally unfair to an optimization algorithm, because we know that the C parameter of the SVM has no effect when you're not using a support vector machine. So that kind of structure in the search space is not trivial to express to an optimization algorithm, but it's actually key to getting good efficiency in search. So that's part of what makes hyperparameter optimization an interesting search problem. And so the way I think of hyperparameter search spaces is actually as directed graphical models. And this is one, I still struggle a little bit to visualize hyperparameter search spaces, but I do think of them as graphs, and they're directed. And this is one. My thinking on how to represent search spaces is that we start with like a model, and then we make choices about how to build it. So a model is this top node, and a model has, in this case, in this model, it has a pre-processing module and it has a classification module. So those are two pieces that we're going to have in our model. Now, what exactly the pre-processing is and what the classifier is hasn't been determined yet. We have this directed process that will eventually tell us how to fill in all the blanks. So the pre-processing is a categorical variable that's like whether we're going to do no pre-processing, normalization, whatever this thing is, a min-max scaling. Oh yeah, that's how to, a different style of normalization. Principal components analysis, TF-IDF, or a standard scaler, which is another module that the scikit-learn library provides. And so this is a categorical choice. And then likewise on the other side of the classifiers, we have like which classifier to use. That's another categorical choice. And so in this case, supposing we choose to do a PCA, then that's going to unlock a couple of more parameters, in this case 2, the number of components, principal components, and whether to whiten the representation that comes out of the PCA module. So you make some choices, you read the documentation, you figure out what are all the kind of possibilities there, and then you produce a large directed sampling process that actually can sample configurations that are reasonable to try. And so I think of that directed model that can generate models that are reasonable to try as a search space. The question then becomes where in that like the person starts by writing down a probability distribution that can generate them from some prior distribution, and the question then becomes how do you refine that sampling process so that it tends to give you points that work well. That's the optimization problem. So now I'm going to take a few minutes to talk about random search and grid search. This is sort of a funny little piece that's pretty short. I wrote a journal paper on random search. I still get a kick out of that. Random search. So what do I mean by random search? Pretty much the dumbest, simplest version of random search that you can think of. So the idea of random search is to write down independent distributions for all of the possible hyperparameters in your search space and just draw randomly from that distribution and try them. So if we want to do a random search of n points, that means we're going to draw n configurations. We're going to sort of put to work our compute cluster evaluating n different places in the configuration space. Every one of them gives us a validation score, and then we take the best. That's using random search for model selection. So this algorithm, I didn't invent random search, and I actually got the idea to use it from Nicholas Pinto, who called this approach high throughput screening. So this is the same algorithm, but I just call it a bit differently. So random search has some convenient properties. Firstly, it's super trivial to implement. Secondly, unlike grid search, you can easily extend experiments by just drawing more points. So on grid search, if you start off with a 2x2 grid or a 3x3 grid, and you try all the points, and you don't like what you got, but you still want to be able to explain what you did in a paper, you have to say, well, I'm going to extend my whole grid by 1 point on one of the dimensions. Then I have a 4x3 grid, so I have to run 3 more jobs to just try like kind of one more thing. And if you have a really multi-dimensional grid, that's really annoying, and it actually requires a lot of computation. In a random search, it's not like that. If you try 50 points in the first place and you don't like what you got, you just try 50 more. And that's still random search of 100 in an unbiased way. One thing which I didn't write on the list of convenient properties of random search is that it's an algorithm, unlike manual search, which is still widely used for model selection. And that's sort of the enemy here. I feel like methodologically, manual search is the unreproducible thing that leads to a lot of fist shaking and so on, as people try to reproduce one another's results, but they can't. Random search still gives you the possibility of getting lucky with one random draw that no one can reproduce, but the odds of that happening are really small, because that's pretty unlikely that you would have got that to happen in the first place. Anyway, random search also has good coverage of marginals. And this is something which is actually the key to the difference between random search and grid search. It's important because, and I'll show you on the next slide a cartoon of exactly what I mean. The reason marginals are important is because of the observation that not all hyperparameters are equally important. So the learning rate in neural networks is really important to get it right. The number of hidden units, not so much. So it's really hard to balance the number of points on a grid of learning rates with the number of points on a grid for numbers of hidden units or some of the other hyperparameters that don't really make as much of a difference. Furthermore, the relative importance between hyperparameters changes depending on the data set. So in the setting where you're trying to, say, provide an off-the-shelf tool that just works on data sets you haven't seen before, a grid search is really a terrible way to do that. Random search is robust to these things, but not grid. So what do I mean by this marginals business? Supposing you have a function of two variables, and the function is a sum of, it decomposes as a function of the first variable plus a function of the second variable. And I've drawn these curves here. The idea is that this green function goes up and down quite a bit, and the yellow function is pretty flat. So if you use a grid to search this two-dimensional input space for a point that maximizes the sum of the red curve and the yellow curve, then you might get in this situation here, where you have chosen 9 points to try, but it turns out you've only really tried 3 along the dimension that actually makes any difference to anything. You've wasted 2/3 of your computation, and this is sort of a best case scenario of 2 dimensions. In higher numbers of dimensions, you waste like exponentially much more work. In a random layout, or some of the other what are called low discrepancy sequences that are used for numeric integration, they're designed so that no matter which way you project the data, you still get pretty good coverage. So if it turns out that only 1 dimension is important, then you're still probably in good shape with random search, even though in grid search it would be catastrophic. And the big advantage of random search over grid search is that you don't have to know ahead of time which of these dimensions was the important one and which of them isn't important at all, because random search has, in expectation, pretty good coverage along every single direction. So to give a kind of perspective on the difference between grid search with human experts, aka my fellow graduate students at the University of Montreal, and random search, which I ran later, embarrassingly. This is a representation of how bad we were at optimizing neural networks, which we're supposed to be good at, for these various different data sets that are kind of based on their rectangles, saying whether they were taller or fatter with neural networks, convex shapes to say whether like the white region was a convex shape or a non-convex shape, and then various variations on MNIST digit classification. So what every one of these figures shows is a box plot for every experiment size of random search. So random search also has the property that it's subdividable. If you ran 100 jobs of if you ran 100 points of random search, you can view that as 10 different random experiments of size 10. And they're all independent. So you can do statistics on them. So what this shows here in this first box here is that with random search of size 1 in the neural network space that we were exploring, this is the distribution on a basic small version of MNIST that we were using for fun. And this is the distribution of scores that you get if your random search has size 1. So this is the distribution of points like in the whole space. There's a few neural networks that get about 75% accuracy, and most of them are up here about 91 or 92. However, if you take the maximum, like the best, across a random experiment of size 2, then these low outliers are typically rejected because the max doesn't pick them. So as you take larger experiments, the accuracy of the model you get by your cross-validation procedure is better. If you take a max over 4 points, then you're pretty reliably getting one of the good performing networks. So what this figure is showing is that even with random search in a 9-dimensional space, where we're trying only 4 or 8 points, we're already really reliably getting something pretty close to the best you can do in the whole search space. For these other data sets, the story is not, I mean, it's the same story, but the convergence isn't quite so fast. Like for this rectangles data set, to get a really robust estimate of what turns out to be what we think the best point, you have to try 16 points on average. For the rotated digits, then it's also 16. For this MNIST background, this is a really messed up data set, and so you needed to try more points to get some kind of good performance there. Now, the two bars going back and forth are the confidence interval, and the best we got with like the 64 points, I think. And the dotted blue line is the human experts. We had used at least 100 points of grid search plus manual optimization as well. And what you'll see is that random is better than us, even though in most cases it's only trying like 16 points. So the embarrassing result here is that 16 random guesses in the search space is better than us when we were trying. So that was a kind of sobering result. In the case of convex, this data set we're way off, and that's because well, I mean, the reason for why this happened was because someone had figured out kind of what was a good zone to try with grid search on one of the data sets, and then just used the same grid for all the other data sets. And that's just was a terrible idea. The relative importance among hyperparameters is the explanation for why it made such a big difference to use random search. What this graph is showing is for those same data sets, and I think maybe 2 more, if we did a kind of ANOVA style analysis of like how important was every single hyperparameter in explaining variance in the performance of our models, then for different data sets, we got that different of the parameters were the important ones. So on the basic MNIST version here, this initial size of the weights turned out to be really important. That's the blue one. And the learning rate turned out to be really important. So there's only 2 variables that explained all the variance, and it was the initial size of the weights, which we didn't really think was that big of a deal, and the learning rate, which everybody knows is a big deal. But for some of the other data sets, like this convex data set, the initial size of the weights didn't make any difference at all, and different of the hyperparameters explained all the variance. So there's no grid that we could have used that had enough granularity in every single category to be good enough for all the data sets and at the same time be feasible to run. The random search was able to optimize these things in like 16 tries. A grid that was sufficiently good would have had tens of thousands of points in it. So after that work, I put together this sort of kind of guide to hyperparameter optimization. Random search here up at the top is complexity, very low. Reliability, pretty good for 2 dimensions, pretty good for 3 to 10 dimensions. More than 10 dimensions, it's still sort of okay. Grid search, terrible. Manual search, very bad. Adaptive search, that's kind of what people usually think of as an optimization algorithm, where it's like you try points, you see what happens, and then depending on what happened, you try different things in the future. Random search is not like that. It's a brute force approach. So that was kind of the motivation for taking on somewhat smarter optimization approaches for trying to tune that 32-dimensional deep belief network, or this HTL3 model is a big convolutional network, a particular kind of restricted Boltzmann machine that I was researching at the time. These all had a lot of hyperparameters, so we needed a different solution to be able to find what worked. And that brings me to the last part of the talk, which is searching large model spaces with the tree of parts and estimators algorithm. Now, before I get into that, I will ask if there are any questions about what I just talked about. Yes?
So if I had to summarize what you just said, manual human search is terrible. And like, I mean, the idea of random search being amazing, but you only have to try 16 random searches, it seems like too much magic from randomness.
All right, so the summary, did everybody hear that? I suspect maybe. The quick summary was that manual search is terrible, and 16 random points will probably work, and that just doesn't seem realistic at all. All right, so to respond to that, I would say the reason manual search was terrible is that it didn't work on 5 out of 6 cases here, because we didn't actually do manual search and grid search independently all 6 times. What we did was do manual search ourselves for the top left-hand corner, and then use our gut instincts to figure out what would be a good grid to try around that point. And that worked really well for that one point if we spent all that effort. And it failed catastrophically on all the data sets that we didn't actually treat with our manual approach. So to say manual approach is terrible is an exaggeration, because it worked in this case, and it still works for the most complicated systems that people still publish on in deep learning. And you know, it's still part of the process of writing an algorithm and understanding how it works, is to run it and see what happens and try and understand what's going on. I don't count manual search as an algorithm, so it's tough to say how it compares in general with other things. And plus, everybody's different. Everybody implements their own version of manual search differently every time they do it. So manual search, yeah, it's not so much terrible as it is not kind of on the same playing field. And for some of these problems also, 16 points wasn't really enough. You can kind of understand geometrically what this is doing. If the volume of the good points you're looking for is smaller than a 16th of your search space, 16 points isn't going to cut it. And different search spaces have different kind of topology that will say how many points you need to try. So the question is, like, was I surprised by these results, and like, what did I make of them? Right. So certainly for this one, I mean, for all of them, the learning rate is a very important parameter, and that was not a surprise at all. That was what our conventional wisdom led us to expect. For some of the other ones, I don't think it was such a surprise, because no one had such a clear idea really of what to expect. Sometimes you see a paper about how such and such an initialization procedure should be used. And they tried it on some data sets and it worked. As a reader of that kind of paper, that thinks, you know, okay, maybe that works for me too. And then that sort of puts some uncertainty as to whether or not that's an important factor. That kind of uncertainty is actually borne out by these results, where on 2 data sets out of 8, the initial normalization of the weights was a factor, but not on the other ones. So it is a bit hard to. Maybe I should just leave the answer at that point. Certainly, you can use this data to guide research into how to design learning algorithms.
But I'm naive if I think that this could possibly lead to an approach where you decompose your search space and optimize differently for different parts.
Right. So this analysis is based on a Gaussian process explanation of, it's not really ANOVA, it's Gaussian process that I used. And what's being shown here are the inverse length scales of a Gaussian process with a certain kernel for each of the dimensions. And indeed, Gaussian processes are a model-based approach for sequential optimization. And so, yes, you can use the same analysis for visualization as for optimization. I was actually talking with Walter before the talk about this. Almost every time you can produce a visualization that helps you see where in the space you should try, that's an optimization algorithm ready to be written. So it's almost the same thing. I would agree. I would agree with that. You're nodding as if you agree also, so that's why I said I agree with that. Yeah. Any other questions? All right, so the last part is what to do when random search fails. Like on this one. So this diagram shows something kind of like the Scikit learn picture, except for this is written for a convolutional network. I worked on this one with David Cox and Dan Yemens. The idea was that there'd be a picture, and then there'd be some processing of that picture, and then maybe some more processing of that picture, and then maybe some more processing of that picture. And maybe you have some max across various features, or maybe you do some normalization, or maybe this, or maybe that. And it's quite a huge search space of possible randomly allocated convolutional neural networks. And so we set up this. This is actually a model that he and Nicholas Pinto and Zach Stone had been working on for some time in the Jim DiCarlo's lab. I arrived on the scene and thought, all right, let's try this hyperparameter optimization business on your big random convolutional networks. And we wrote all the parameters out, and it had something like 238 hyperparameters. Now this is the same model that was actually used for the high throughput approach, the high throughput screening. And you know, the fact that it worked as well as it did was the reason I investigated random search in the first place. So random search kind of works for this type of model. I should note that this convolutional network has no backpropagation, so it's not like a convolutional network in the usual machine learning sense of the word. There was a paper earlier in the conference by Giovanni Ciaccia and co-authors where they were using this type of approach for recognizing license plates. So how are we going to search this kind of a space? The answer that I looked at was Bayesian optimization. So this in one slide is the optimization algorithm that was kind of anticipated by your question about those Gaussian processes. So Bayesian optimization, or what's called sequential model-based optimization, is a strategy for optimizing in a space where it's kind of like the last resort. You have hardly any idea what's going on. It's a big space, and all you can do is try it in a point, see what kind of a score you get, and then go back to the drawing board. There's no gradients. It's not necessarily smooth. And typically these approaches are used when the function evaluations themselves are quite costly. So like manufacturing processes, or drilling for oil, or those kinds of things where to actually make a measurement costs a lot of money. These kinds of techniques are used for figuring out where exactly to try. The idea in a Bayesian optimization approach is to build a statistical model. So you're doing machine learning like in the loop. You build a statistical model of what you've observed so far about the hyperparameter search space. So what I'm showing here on the horizontal axis is hyperparameters. So you can imagine this is like the C parameter of the SVM. On the right, we tried a C value along with a whole other bunch of values, and we got this score up here. Validation cost is increasing. This score, you know, we tried it. We didn't really have much context to decide whether it was good. We tried this one over here. It was about the same. Tried this one here. Often these approaches start by random search to get started, and then you build a model that goes through all points and is a statistical model of what to expect in terms of performance across the entire hyperparameter space with some mean and variance estimators as well. And then the idea is to take that quickly fit model on a couple of observations, and then look for points in the space where the mean is pretty low, but there's some variance around that estimate. And then there are various criteria for how to turn that spirit into an actual number that you can optimize, and expected improvement is one. So expected improvement means the expectation below this best observed point. So if you look at the expected improvement across this cartoon diagram, you'll see that this point has so much uncertainty that it might be worth trying. This point has less uncertainty, but we're pretty sure it's pretty good. So it's actually the best point according to the expected improvement criterion. And this point here is slightly less good. These ones over here, we're pretty sure that they're bad, so we're not going to try them. So the idea of building this kind of model is that you sequentially build this model, do a numeric optimization of the red curve, and then you try one point. And then you observe what happens, and then you build a new model, do another optimization, and try one more point. So it's a very slow, heavy-duty kind of optimization procedure. But since training deep networks is also really slow, we figured it was worth it. So the kind of sequential model, the algorithm in a nutshell is the same thing. So you start with no history at all, and then until you get bored, you build a model, and then do a numeric optimization and try one point. My algorithm for doing this, and I'm going to skip over some important previous work, I'm sorry. My algorithm for doing this is called the tree of Parse and estimators. It's not based on Gaussian processes. It is based on building two densities by dividing the observations into two sets. You take all the good ones, and you take all the bad ones. So this would be like, this is a good one, these are bad ones. You build a density of where the good points are, you build a density of where the bad points are, you take the ratio between them, and that's related to expected improvement as well. And building densities is a lot faster than training Gaussian processes. So that's why this algorithm can be interesting. And using this kind of approach on the giant convolutional network in this slide here, I didn't try it on MNIST first, but everyone tries it on MNIST, right? So I ran MNIST. And in about 6 hours on a couple of GPUs, maybe 4, this approach was able to get a state-of-the-art number on MNIST, better than the Jan LeCun's models that he'd been building for 20 years. It was very surprising. So hyperparameter optimization for the win on this one. A couple of other data sets we used. PubFig83 is a facial recognition data set. And so here, TPE is much better than random search. LFW as well. LFW has the flavor. We can actually compare with the human expert optimizing within the same space as we were searching. So the space I chose was chosen to kind of include the approach of Nicholas Pinto, and as well a similar network designed by Adam Coates that had been shown to really work on CFAR10. And so what this is showing is that the tree of Parse and estimator quickly found a better score in validation than Pinto and Cox ever found, and a slightly better score in test. This one also on CFAR10 kind of matched Adam Coates' performance, although we beat him in validation quite a bit. So beating on validation means that we're kind of overfitting to the validation set, and that's an issue with this kind of approach. We can also look at the results afterward to try and understand a little bit about, like, what do these giant convolutional network search spaces look like, and start to answer some of those scientific questions about, like, what kind of models are good for vision. And I saw a talk this morning about visualization at the visualization workshop, which was inspiring, because I find these things still pretty hard to read, even though I made them. What this is showing is that for 5 different data sets, and 3 different kinds of features that you can pull out at 3 different numbers of layers. This is showing that, like on the house numbers data set, pretty much no matter which kind of features or which number of layers you pick, it kind of doesn't matter. That is actually not an explanatory factor of variation in this data. For facial expression data, 2 or 3 layers is way better than 1 layer. But for object recognition with the CFAR data set, it's the opposite. So only 1 layer is doing much better than the 2 or 3 layer models. This other face data set has 2 or 3 layers as well. So you can kind of look at the data in different ways to try and understand, like, what kind of deep networks are effective on different data sets. And so far, there isn't really a clear picture emerging that a certain depth is good, or a certain kind of like pooling. That's not really the thing that seems to be explaining goodness. Here we're looking at different approaches for initializing filters in the middle of a giant convolutional network, and again, not a clear winner between randomly allocated filters or filters that are obtained by looking at the data. So no strong positive answers there, but at least a tool for investigating those questions. We also did some experiments more recently on hyperparameter optimization in scikit-learn, and we were more pleasantly surprised. Here we were able to search like through 6 classifiers and a bunch of pre-processing algorithms, and we were able to search the whole space, and in a fairly small number of jobs, rival the best answer you could get by searching only within the kind of classifier that turned out to be the best. So it didn't cost you anything to search the whole space, sort of the take-home message. And that's really good for being able to provide an off-the-shelf tool that does classification. 20 news groups and convex is some toy data sets that we looked at. The performance is quite competitive with the literature. This was all carried out with a tool called Hyperopt, which is another Python library that is up on the web. You can check it out if you're interested in doing some of this kind of explorations in your own work. There's a lot of ongoing work and future work to do with hyperparameter optimization, building bridges to existing software packages, such as SMAC and Spearmint, that do sequential optimization based on regression trees instead of, or Gaussian processes instead of the TPE system. Designing kernels for doing Gaussian process optimization in hyperparameter spaces is really hard. Visualizing things, visualizing a performance in a 238-dimensional space is it continues to be a difficult thing to do. Dynamic allocation of computation during search. So how do you cut off long-running jobs based on partial feedback about how well they're working? That's an open question. Building in a convolutional network that has all the latest tips and tricks is a work in progress. And yeah, just basically using this library for more different kinds of things. So to summarize the whole talk, deep learning requires lots of data, and you need to use GPUs. Neural nets have actually not changed that much since the 1986. And Theano makes deep learning easier to program, and so I recommend certainly using either Theano or Torch in your own explorations in deep learning. Deep learning approaches have a lot of hyperparameters, and so you need to have some experience in how to set them. You can either use a tool like Hyperopt, or you can read through those tips and tricks guides, or ideally both. Bayesian optimization is sort of emerging as an automatic technique for doing model search in these huge spaces. Grid search is terrible. You shouldn't use it for anything. Hyperopt provides a language for domain priors so that domain experts who have been using SVMs for years can say in what circumstances and with what probability they think that different kernels and different configurations and so on should be chosen at the outset. And finally, it provides algorithms for actually carrying out optimization after those priors have been set. I want to thank several people for making all this work possible. My advisors at University of Montreal, at Harvard, and Waterloo, as well as colleagues Olivier Bergstra, who worked on Theano, Frédéric Bastien, who's still an ongoing Theano maintainer and evangelist, Dan Yamins and Nicholas Pinto at MIT, and Brent Comer at Waterloo, and David Ward-Farley at University of Montreal. And these funding sources as well made all this possible. So thank you very much for your time. That brings the talk to a close. And so if you have any questions about that last part, now is the time to ask. Thank you very much.
I think my question is more has to do with the first part. I wonder, you said that some of the problems you can solve with not many hidden layers. I wonder how deep you need to be the networks to solve. I mean, does it depend on how big is your data?
The question is, how deep should networks be?
Yeah.
I don't think anybody knows the answer, but typically you're right. With more data, the answer might be more than it was with less.
I mean, more is, I mean, can you give us an estimate of number? You're working with 10 layers, 20?
That's right, yeah. I've heard people publish results with as many as 7 to 10. Okay. Sometimes the convolutional networks have several layers of convolutions, and then there's a couple of fully connected layers on top of that. But it's extremely data dependent.
Thank you.
Yeah.
Is there a strong motivation for using the Bayesian framework for tuning the weights and the hyperparameter space? And I mean, did you try to compare the performance of the TPA with genetic algorithm, for instance?
Yeah, this is a pretty wide open and new kind of optimization problem. And so any technique for black box optimization is pretty much on the table. I haven't tried genetic algorithms, but I think they could be good.
Thank you.
Anybody else?
I was wondering which kind of applications can you have for deep learning, like, for example, try to cross data from seismic studies to oil drilling, for example. Is it possible? I mean, I just want you to talk more about some specific kind of applications that you can visualize for this kind of thing.
So what deep learning, like the connection between deep learning and existing machine learning techniques is about feature extraction. So if you had a problem on the table already that involved using some features to condition some kind of inference, like a classifier or like a hidden Markov model or some kind of other Markov random field or whatever you have, if you already have features and you wish you had better features, then deep learning might be the answer.
Okay.
But it might not be as well, because it's really hard to train them. That's where the data comes in. Yeah.
Thank you. Do you have anything to add for the class?
Oh, guys, the bus will be downstairs, and the closing session will be held at the museum. Then the transfer will be being organizing downstairs. For who do not have yet the dinner tickets, please, I'll be downstairs as well to organize that. Okay, just see you soon. Yeah, I did. I got it. Oh, yeah.
Som.